Jai Hind everyone. I am Dr. Nitya Sharma, Assistant Professor, Ajay Kumar Garg Engineering College. I welcome you in my next lecture, IR Spectroscopy, Reasons of IR Spectroscopy and some reasoning questions in regarding the IR spectroscopy itself. So, today we start with the which of the following molecule will be IR active. These are the some basic questions. We will start with part that what is your background about the IR. So, what is requirement of IR to be a molecule to be IR active? So, first we see that. So, here what is the which of the following molecules will be IR active? So, what is the requirement of a molecule to be IR active? That molecule must possess temporary dipole moment during the vibration. Temporary dipole moment during the vibration means as here example is nitrogen. Nitrogen which is having zero dipole moment. So, it will be what? It will be IR active or not? No, it will be not IR active. Then carbon dioxide. Carbon dioxide, it is no permanent dipole moment. This is temporary dipole moment. So, when it vibrates, then dipole moment changes according to it. So, carbon dioxide change in dipole moment occurs. So, it is IR active. Then OCS, this is having permanent dipole moment. Whenever the permanent dipole moment is there, then the molecule will not be IR active again. H2O, temporary dipole moment, it will dipole moment changes only at the time of vibration. So, H2O is again IR active. CH2, CH2. This CH2, CH2 molecule and CH molecule, those are symmetrical molecule and they can be cut into two equal halves. They are as similar as any homodiatomic molecule. So, this is again not IR active. Then C6H6, yes, C6H6 shows IR activity, rather it is a symmetrical molecule, but it is also having different kind of vibrations. So, it shows it is IR active. Then more often one question is asked, methanol is a good solvent for UV visible spectroscopy, but not for IR determinations. Why? So, when we talk about the solvent, what is role of solvent? Role of solvent is to be inert in the atmosphere and let the solute show its properties. In case of methanol, what happened? It absorb the UV do not absorb UV spectroscopy because it do not having any chromophore, but methanol it is CH3OH. So, this bond all are IR active. This shows IR active vibration. So, it itself shows IR activity and thus it is not good solvent for the IR determinations because it do not remain inert in case of IR spectroscopy. So, when we see the IR spectroscopy, it is so jumbling, it is so confusing type of structure we found that in this IR spectra, this is original IR spectra of ethanol. So, we have to determine what is the we will study in this this video that how we study this spectra. What does the spectra tells us? This is spectra. It is about the vibration in the bond. So, this bond, this is molecule of ethanol, CH3, CH2OH. So, this is oxygen, this is hydrogen, this is C, one H, another H, another H, and this is C. This is H and this is another H. So, this is molecule, different kind of vibration do takes place, and when these vibrations go through the IR spectra, this is a setup of the IR and we get the spectra like this. So, how we will interpret this spectra, what these regions are found, we will see. Then there is a formula. Actually, when we talk about the IR spectroscopy is simple vibrations, simple vibrational spectroscopy. What does it mean by vibrational spectroscopy? That there is vibration do takes place between the two bonds which are associated with each other. This bond is like spring, and when this spring vibrate, it shows simple harmonic motion. Simple harmonic motion, when there is simple harmonic motion, it is given by the frequency is given by the formula nu bar is equal to 1 upon 2 pi c root k by mu, where c is velocity of light, k is force constant, it depends on how strong is the bond. As for example, C triple bond C, which is having higher bond strength, K will be more than C double bond C, then say single bond C, and so on. Mu is reduced mass. Reduced mass is equal to M1 M2 upon M1 plus M2. M1 and M2 are respective mass of two atoms in which we are discussing the frequency. So, when we talk about this frequency and this formula, so we can find a specific frequency designation which is obtained from this formula, and thus when we verify it with the functional group with the reasons where we got the structure like this. So, we got COH stretch at 3391, CH stretch approximately 2981, and similarly CO stretch and OH and furthermore. So, basically when we talk about all these, so we got these kind of regions where the regions are, this is referred as functional group region, this and up to this is known as functional group region. What are functional group region? Whose valencies, whose bond strength are fixed. When we are talking about OH bond, then O is fixed, hydrogen is fixed. So, we can determine the frequency by the formula nu bar is equal to 1 upon 2 pi c root k by mu. So, when we talk about this k and mu, and we can find out a mean frequency which is known as wave number here. So, by this determination of wave number, we can find out the average frequency. But in this complete portion of a specific single one bond like CH bond, if I talk about the CH bond, only variable is K. K is the force constant. Force constant means how one atom is attached to the another atom, how forcefully they are attached with each other, how much attraction force is in between them. So, what will happen? This CH bond, just one example, CH, but the frequency K will be vary. So, when K will be vary, we are having different values of K for the different compound, yet still they will remain in this region only. When I am talking about CH single bond, thus we get the frequency region in this region. Similarly, when it is triple bond, the region is this. If double bond, region is this. So, this is referred as functional group region. in which we can find out the mean frequency, mean specification. We have to learn it. Then it comes to the single bond. This is known as fingerprint region. What is fingerprint region? So before that, so fingerprint region, by which IR spectroscopy is referred as fingerprint of the molecule. What is fingerprint of, why it is known as fingerprint of the molecule? Because no two persons are having the same fingerprint. Similarly, no two molecules will show the same IR spectra. No same IR spectra, it means overlapping IR spectra. So what actually happens? Why this is known as fingerprint region? So we are talking about the ethanol. Here is a one derivative of the alcohol, that is butanol. We are having similar frequency of OH stretch nearby in between 3500 to 3000. Then this is saturated region of CH bond. This is CO stretch nearby 1700. But this overall region is so much complicated. Bonds are very much interacting with each other. The total vibration, it is quite type of bending. It is combination of bending vibration, symmetrical stretch and asymmetrical stretch, all of these. So this is having a complex pattern. So this complex pattern in between 1400 to 600 centimeter inverse of frequency is known as fingerprint of the molecule. And if it is being said, if the IR spectra are same in case of fingerprint region also, then it is a rule that two molecules are the same. So this is our fingerprint region. This is very much complex. So what are the points here? So the range is in between 600 to 1400 centimeter inverse. This is a complex. This is formed by the bending vibrations and symmetric stretch as well. And a quite large number of peaks we have seen in the fingerprint region. So this is infrared spectra of IR spectroscopy. Yet the previous knowledge we have seen this bond, we can refer that this bond will belong to the OH frequency. This bond belong to the here it is nearby 1700. This is OH and this is fingerprint region of, in fact, a simple molecule of IR itself. So this is average position of some important frequency which you have to learn for the simple example, for solving the simple example, simple reasoning questions of IR spectroscopy for the BTech first year students. Specifically, these are the mean, I am saying that this is average position. Average position, what are the factors on which it depends? It depends on number one, inductive effect. Number two, mesomeric effect. Number three, hydrogen bond. So in short, what we can say, this frequency, this variation can be done, will be experienced by a molecule whenever there is a change in the environment of that particular bond. A slight change will differ in any of these points. It may be resonance. It can be said basically stability factor. The molecule, one which is stable, we know the basic formula, that is E is equal to H nu and E is equal to Hc by lambda. So by this formula we can infer whatever this energy difference, this is basically all energy gaps. So whatever the factors, stability will increase, that energy gap will be reduced, frequency will reduce, and similarly we can find out in this pattern. So here what is the main point here is average position. What we have to learn it, that OH frequency, the mean position is 3600 centimeter inverse, C double bond O 1700 centimeter inverse, C single bond O 1070 centimeter inverse. Similarly, we can see here very clearly that triple bond CH at 3300, double bond CH2 is 3000, single bond CH3 at 2100. This is this because K is decreasing, so nu bar is decreasing. We can find out. So, for learning purpose, we can say that we have to learn this mean value 3000, above which, and again one thing to assure, this is again average position. So, it will change from molecule to molecule. So, this is a 1 point. Now, similar pattern we can find out in case of carbon-carbon single bond, carbon-carbon double bond, and carbon-carbon triple bond also. In case of amines, in case of NH, the frequencies obtained is in between 3500 to 3100. Only the variation when there is NH, it is tertiary amine, then we will tertiary amine we will got no signal. If this is secondary amine, we will got 2 signals, and in case of primary amines we will got 3 signal in this region only. So this is how we interpret the functional group, what kind of functional group is present in our molecule. So this is example of hydrogen bonding. Hydrogen bonding in this case, where this is hydrogen bonding, the energy get lowered, and when there is no hydrogen bonding, energy is higher of C double bond O. Which bond is we are talking about? This bond. So because of this, hydrogen bonding frequency is getting lowering. So wherever the hydrogen bond is there, frequency will lower. And another, if there is one more thing, we will discuss it later on. So this is again example of hydrogen bonding. How the hydrogen bonding changes with the dilute solution. When there is concentration solution, this frequency range is 3550, and when there is dilute solution, the frequency rise. This is as the hydrogen bonding is increasing, so this frequency is also increasing. Now, the reasoning part, the major part, which is slightly tricky, but once you remember the peaks, where the peaks are, where it belongs, then you will find out how this is possible. So, I have taken the questions which are in previously asked question in AKTU. So, determination of structure of compound C3H6O shows the following absorption band in IR spectrum. The first at 2950 and second is 1720. Only clue other than this given is this is give negative test with the tolerance reagent. So what are the reaction? What are the procedure? We will find out the structural formula. So first write 3 carbons, then 1 oxygen. It can be if I am putting oxygen and number of carbon 1, 2, 3, 4, 5, 6 hydrogens, and 1 oxygen. This is one structure 1. Another structure which is possible, I put this carbon-carbon double bond in center. And putting rest hydrogen. So, by the formula C3H6O, only two structural isomers are possible. When I am talking about these two structural isomers, one is aldehyde, another is ketone. So, any of two is possible. So, which is that? We are having a clue that it gives compound gives the negative test with the tolerance reagent. Tolerance reagent, it is a specific test for the aldehyde. If it is aldehyde, then it will positive test with the tolerance reagent. So, surely we are having the compound which is ketone. So, next, a compound having molecular formula C2H4O2 while studying for IR analysis result in the following peaks of spectrum. So, we are having 2900, 2950, then 1710. And we are having, so first what we will do, C2H4O2. Then IR spectra, it is 2900, 2950 centimeter inverse, then 1710 centimeter inverse, and 3500, 3650. So, if we know the pattern, then we can say this is identification of CH bond, this is identification C double bond O, and this is identification of OH bond. The compound give also effervescence with the N2CO3. So, this is another part. So, we will try to find out the structure. This is C2, 2 carbons, 1 oxygen and 1 OH, rest hydrogen, 1, 2, 1 hydrogen, 2 hydrogen and 3 hydrogen. So, total number of 4 hydrogens are there. Total number of 4 hydrogens, we can count it here. So, how we can find out how can verify the structure? This belong to this. I say this is peak A, this is peak B, this is peak C. So, this belong to peak A, this belong to peak B, and this belong to peak C. We know that's OH structure, OH specification we find at the 3500 to 3650. So, this is mean value of this OH bond. 1700, we have seen the average frequency of C double bond O bond, and CH nearby the 3000 mean value we have taken learn the 3000. So, it is like that. Now, the next point, next question. So, an organic compound having molecular formula C7H6O shows absorption peaks at 3010, 2700, 1600, 1580, 1520, 1480 and 1720. All lots of peaks. So, this must be quite very difficult, some kind of thing. Is it so? Let's see. So, how many peaks we determine now? We know now rather. So, we know this 1720. 1720 belongs to C double bond O. 1720 belongs to C double bond O. We little bit know about these frequency. This is of the CH bond 3010 and 2700. It is CH bond. Now, these 4 frequency about which we do not know yet. This is in fingerprint region. And again, these frequencies are fingerprint of presence of aryl molecule, presence of benzene ring here. So let's see if we find something including this C7H6O. How many carbons are there? 7 carbons. How many hydrogens are there? 6 hydrogens. So can we find out something fishy about it? Number of hydrogen. This is totally unsaturated compound. Oh yes, this is benzene. This is having Huckel. This is showing the Huckel rule. So 1 is benzene. So how many carbons are here? Total number of carbons? 6 carbons. 6 carbons when attached with a ring. Then we are having C double bond O. C double bond O is directly attached, or total number of carbons are completed here? No. Total यहाँ पर 1, 2, 3, 4, 5, 6 carbons. So next one is one more carbon, or we are having structure C7. Now hydrogens, are they completed? We are having one hydrogen here, 1, 2, 3, 4 and 5. This carbon will not having hydrogen. This is attached to the carbon. So this is displacement. So one hydrogen here with this carbon, valency of this carbon is not satisfied. This is oxygen. So yes, it is benzaldehyde. So this is benzaldehyde. We found a simple molecule with so many data here. So here it is. What again we have to find out. We have to learn the basic structures of these, all these. Now these kind of ocean. How will you distinguish between the following pairs of spectroscopy? Number 1, ethanol and propanol. Ethanol and propanol, when we talk about the ethanol and propanol, ethanol is CH3, CH2OH. Propanol is C double bond O. Same formula, same molecular formula, different molecules. How we will differentiate? We are having peaks of OH characteristic frequency nearby 3600 centimeter inverse. This frequency, characteristic frequency nearby 1700 centimeter inverse. So simple observation. Then the second one, phenol and cyclohexanol. Phenol and this is cyclohexanol. Yes, CH bond. Which one have the higher frequency of CH bond? It is cyclohexanol or it is phenol. We have seen that one is having C double bond CH group, and this is single bond CH. So as inductive effect properties, inductive effect properties are what? Whenever we find this, then the frequency will lower down, and so we have seen that frequency of CH is lower than compared to the double bond CH, because K value, whenever K value decreases from the double bond to single bond, the frequency will also decreases. So we are having this frequency at the lower level. Similarly here we are having phenol. The characteristic of phenol is 3600 centimeter inverse. This is another criteria. Cyclohexanol, sorry, this is cyclohexanol. So cyclohexanol, we are having this frequency, but in this case, both the case, the frequency of OH will be again shifted, and so we can find out what is the difference between the phenol and cyclohexanol. So next is acetaldehyde and acetone. In this case, acetaldehyde and acetone. Here there is a characteristic frequency of this bond. This is acetaldehyde, CH3 CH. Acetaldehyde, in case this is aldehyde, CH, and acetone, that is C double bond O, here CH3 group, here CH3 group. So in case of CH3, in both characteristic frequency we will find out this molecule, but one CH in case of acetaldehyde will be downfielded. Downfielded means that it will be from the lower side of the field. Then in case of acetone, and in case of acetaldehyde and acetone, we got the overtone in case of aldehyde. So by the overtone which is occur nearby the 3400, we can find the difference. Then the next one is alcohol and ether. In case of alcohol, there is a special peak that is at 3600 at in case of alcohol, and in case of ester, we will have no peak at OH. The next is orthonitrophenol and paranitrophenol. Orthonitrophenol and paranitrophenol, and these 1 and 2, these are having the same differentiation, because one will have the intramolecular hydrogen bonding, another having intermolecular hydrogen bonding. Orthonitrophenol, this is orthonitrophenol, and this is paranitrophenol. So this molecule will show intramolecular hydrogen bonding, and this molecule will show intermolecular hydrogen bonding. So with the help of hydrogen bonding, we can find out the difference between the two. In case of where the intermolecular hydrogen bonding, this intermolecular hydrogen bonding will show a quite broader peak at 3600 of OH. Nearby 3600, we are having quite broader peak, and in case of intramolecular, it is quite lower peak. Similar case can be done with the help of in this case. So thank you for this time. You may ask your questions in the comment box only, and welcome for the next PPT. Thank you.